All right, hello everybody. Today we're going to learn a new function. And like I normally do before I introduce something new, I like to go over what we already know about functions and what we've already learned and find a way to tie it all in together. So the very first function that we learned was called the linear function, which was modeled as y equals mx plus b, or f of x equals mx plus b. And the characteristic of that, of course, is the graph of it is a line, and it represents constant rate of change. So an example of that is if we had a situation like Robert's swimming pool has 5,000 gallons of water and is filling at a rate of 1,000 gallons per hour, the way we would model that would be y equals 1,000x plus 5,000, because the constant rate of change is 1,000 for this pool. If we look at our next function that we learned, it was f of x equals ab to the x, where a is our coefficient, b is the base, and x is going to be the exponent. And the characteristics of this is it was an exponential rate of change or repeated multiplication, and it was represented in growth and decay models. So an example of a growth model would be the city of Newton Grove begins with a population of 600 and doubles every year. So we would write f of x equals 600 times 2 to the x, because 2 indicates doubling, x would be the years. Then we have a decay model, where we say Miller purchases a car for $10,000. It depreciates at a rate of 7% per year. So f of x would equal 10,000 times 0.93 to the x power, where again, x would represent our number of years. And then if you look over to the left of the slide, we see what the graphs look like for exponential growth and for exponential decay. So the quadratic function. The quadratic function represents something that is in continuous motion. So if we look here at this example of Tommy, it says here, Tommy throws a ball in the air. The height of the ball travels is a function of the amount of time the ball is in the air and can be represented by the function h of x equals a negative 16x squared plus 64x plus 5, where x is the amount of seconds in the air. How high will the ball be after 1 and 3 seconds? After how many seconds does the ball reach its maximum height? So if you notice, we took that function and all we did to find out how high the ball would be after 1 second is we substituted a 1 or input a 1 every place we saw an x, and we did our math, and then that gave us an answer of 53. So after 1 second, the ball will be 53 feet in the air. If you look at the next example, after 3 seconds, same thing, you input 3 into the function, so h of 3 is going to equal a negative 16 times 3 squared plus 64 times 3 plus 5. And again, we do the math, and we get an answer of 53. So we would conclude after 3 seconds, the ball will be 53 feet in the air. Then the last question is, after how many seconds does the ball reach its maximum height? So if you look at the height of the ball, where it reaches its maximum and then changes direction, that is at 2 seconds. Because if you look where the parabola, which is the characteristic, where it curves from going up to going down, the maximum point is 2 seconds. Okay? And then if you would look at the graph, you would see that after 3 seconds and after 1 second, the ball is just about at 53 feet high. So that's what a quadratic function is. So what I'm going to do now is we're going to go to another page and do some guided notes on the parabola and what it means. All right, so what I would like for you to do now is to pause the video and to make a copy of these guided notes for yourself. All I want you to write down is the top portion, the y equals, parabola opens, the table of values, domain and range, the graph, and then the portion about vertex. Do not write anything about the axis of symmetry. We will do the axis of symmetry tomorrow. I'm going to pause the video, and I would like for you to pause right now and just recreate this in your notebook. Okay, so hopefully you've had time to recreate this. So let's start up at the top where we see that we have y equals, and underneath it says standard form. Now, we learned this before when I taught you about polynomials, is that the standard form of a polynomial is ax squared plus bx plus c. And that's the standard form of a parabola. So if I give you the following function for a parabola being x squared minus 2x minus 3, okay, the first thing that we want to determine here, what we want to look at is, make a little bit better of a 3 there. All right, so the first thing we want to look at is what our table of values is going to be. So this here is a set of inputs and outputs in ordered pairs that I've put together to illustrate how the parabola is going to look. So please just write these down with me. So we start with -1, 0, 0, 3, 1, -4, 2, -3, and then 3, 0. All right, so that there is our table of values. So what we're going to do now is come over here to the graph, and we're going to graph these ordered pairs. And like I said, all of these inputs and outputs come from inputting and outputting those values in this function that I gave you. So let's start with the first one, -1, 0, which is going to be right here. Then the next one is 0, and that should be 0, -3. I'm sorry. It should be 0, -3. So 0, 1, 2, 3. 0, -3 is right there. And then 1, -4. So I go over 1 and come down to -4. And then 2, -3. So I count over 2, come down to -3. And then 3, 0. I go over 1, 2, 3. And right there is 3, 0. So I can already look at my points and tell what this parabola is going to look like. So if I just simply connect my points, okay, if I connect my points like that, we notice first of all that the parabola opens up. And if you also notice, my a value in my function is positive. So since that a value is positive, a positive parabola or positive a value is always going to open upward. Okay, so the vertex is right here, just like we saw with Joey throwing the ball. The vertex, actually it was Tommy who threw the ball. The vertex is right here. That's your turning point. So when we look at Tommy throwing the ball in the air, when his vertex was at the top of the parabola, it was a maximum. So that means when here it's right there at the bottom, that one's going to be a minimum. Okay. We also have, and I'm going to make these a different color. This is going to be a x-intercept, which means it's a point where my parabola crosses the x-axis. This is another x-intercept because it's a point where my parabola crosses my x-axis. And then, let's get yellow. This is going to be a y-intercept because it's a point where my parabola crosses the y-axis. Okay, so we'll go a little bit more in depth into those later on in the week, but right now we just need to identify what they are. Okay, so the last thing we're going to do is write our domain and our range. So if you've done the Helen Keller person puzzle, you should know how to write a domain and a range. So the domain is all of my x values. So I've got from least to greatest, -1, 0, 1, 2, and 3. And then for my range, if you notice I have 0, -3, 4, -3, 0. So since some of those numbers repeat, I need to list them one time. And I always list from least to greatest. So I'd write -4, -3, and 0. Okay, so that's the anatomy of a quadratic function. And that there is a positive quadratic function and the parabola opens up. So what I want you to do next is, if you need to, pause the video so you can get all of this down. If not, let's go over to the next page. And I would like for you to make another one of these. Same thing as last time, just simply recreate the top portion and the vertex. Don't worry about the axis of symmetry or the other portion. So I'll pause while you do that. All right, so for this anatomy of a quadratic function, this time we're going to work with a negative. So we're going to have -x squared minus 4x minus 2. All right, -4x, -x squared minus 4x minus 2. Okay, so if you look at what we already learned, if we had a positive happy parabola, that one opened up. So this time we have a negative parabola, so that one is going to open down. Okay, we can just conclude that with our logic, that if a positive opens up, a negative is going to open down. Okay, so for our table of values this time, let's list the following ordered pairs. So I have -4, -2, -3, 1, -2, 2, -1, 1, and then 0, -2. All right, so those are going to be my ordered pairs. And let's go ahead and graph those. So we'll start with -4. So 1, 2, 3, 4, 2, which is going to be right here. And then I've got -3, 1. So I'm going to go 1, 2, 3, 1. And then I'm going to do -2, 2. So I go over -2 and up 2, which puts me right there. And then over -1 and up 1, which would put me right there. And I made a stray mark, so let me erase that. And then my last one's going to be 0, -2. So here's 0, and there's -2 right there. So again, I can judge by my points that I already see that this is going to be a parabola that opens downward, and my value my A value is a negative, so it's going to open downward. Okay, and so we have the same things with this parabola that we had with our other one. If we look first of all at the vertex, which is our turning point, is this one going to be a maximum or a minimum? Since it's at the top of my parabola, just like Tommy throwing the ball, this one's going to be a maximum. My turning point this time is a maximum. Okay, so then again, I can label my y-intercept, which is where this parabola crosses the y-axis. And then I can also look at this and label an x-intercept right here. And then another one right here. All right. And then, like we said before, This here is the vertex. Try to cram all that in. Okay. So that's the vertex. All right. So this is everything about the anatomy of a quadratic function. So what we looked at today is where a quadratic function is used, what the standard form of a quadratic function is, that when a parabola is got a positive a value, it's going to open upward like this one. When it has a negative a value, it's going to open downward like this one. When it opens downward, the vertex or the turning point is a maximum. And when it opens upward, the vertex or the turning point is going to be a minimum. All right, so what I want you to do now is you'll find on your Google Classroom a Desmos activity called Will It Hit the Hoop? And it's going to be an opportunity for you to explore parabolas as it relates to the game of basketball. So this is it for today. Please do the Will It Hit the Hoop activity, and I will talk to all of you again tomorrow.